Hello everyone, I'm Selena, and in this short video I'm going to briefly introduce the Boyer-Moore-Horspool algorithm, including giving several examples and a short explanation of the complexity of this algorithm. And I hope you can have a clear picture in your head after watching this video. And by the way, please try your best to ignore my English and grammar mistakes, because English is my second language. I'll be really grateful. Thank you. So now let's start. We'll start from what is BMH. It is actually an algorithm that used for the string matching, and it was published by Boyer-Moore-Horspool in 1980. If you have ever learned about string matching, you may know about the Boyer-Moore-Horspool algorithm. Why did I mention here? It is because this algorithm works quite efficient when the alphabet of the string is really small and have a lot of repetition in the text. When it comes to a bigger alphabet, this algorithm doesn't really work. So what we need is an algorithm to solve this question, and BMH is the first choice. So what I'm going to do now is not going to throw a whole bunch of theories on your face. I'm just going to give you a small example to let you understand how BMH work. So here is the string. The green text is string and the blue text is a pattern. So our common sense tells us that if we want to compare the string, and we need to first start from the left, right? But this algorithm is totally different. We need to start from the right. So we compare R and A. Here we go. So it's obviously mismatched, right? And we are not going to keep comparing because it's useless. We already know this mismatch, and these three letters are definitely mismatched too. That's my idea of this algorithm. We are going to escape these three letters. So we are going to keep moving on and align E and E here. So we have S and A. Again, start from the right, remember. S and A, mismatch, keep going. And I and A, mismatch, keep going. E and A, mismatch. But now, please notice that E is actually exists in the pattern. So we really don't want to escape this letter because we may find ourselves miss something really important. And the truth is, it's going to match if we skip it, the whole algorithm is not going to work. So what we are going to do now is to move the pattern to align with E, and because this E is in the first letter, we are going to align the first letter with it. Here we go. And now we start to match from the right again. A and A match, X and X match, E and E match, perfect. So we know the answer now. So what can we summarize from this algorithm? Here is the main idea. We actually use the alphabet that makes up the pattern and input text to escape large distance, and we make compression starting on the right of the pattern rather than the left. This finds the rightmost mismatch. So how can we achieve this algorithm? To achieve this algorithm, the most important part is to remember the shift step, right? So to remember it, we need to build an array. I don't know how to pronounce this symbol, so I will just use a table to represent it. Okay, so we need to build a table to store the rightmost occurrence of each letter in the pattern. So let's let the strings alphabet be C0 to CK. The table I will store the rightmost occurrence position in the pattern of the letter CI. You may be a little bit confused now, so I'm going to show you how this actually works in an example. This is the one that I have shown you before, right? So the alphabet of this text is HERSAMPX. Okay, and the table that stores the occurrence of the rightmost letter is showing here. So you may ask, how can you get all this value? Okay, so what we are going to do is to actually compare the alphabet letters to the pattern letters and trying to find whether it exists or not. If it is not, we are going to give it a value, and in this case we give it -1. So why we don't give it value 0 or something else is because when you actually try to write the code by yourself, you'll find it. Using -1 is really useful to find out the matching position. Okay, so we got H here is not exist in the pattern, so we give it value -1. E exists, so its position is 1, so we have position 1, and R position -1. Because it's not exist, I -1, S -1, A exists, it's position 3, so it is 3, M -1, P -1, and X 2, right? Okay, so then I'm going to show you the pseudo code here. I wrote it by myself, and what we have just learned is actually the initialize table step. So we have a table store all the positions, and now what we need to do is to calculate it. We have position equal to 0 to initialize it, and we have a while loop to make sure that the pattern didn't get out of the string, so that doesn't work, right? So we have J here. J is actually the position of the letter in the string that we are comparing now, and we let it equal to the pattern size -1, and we got another while loop here. If the J is bigger and equal to 0, and the array P, this actually it is the strings array that store all the strings letters here equals to the patterns array, which means that we got a match, and we let J -1 here, and if J is less than 0, we got a break. So the last code is used to calculate the right position, right? And we return POS finally. So because time is not enough, I'll just let yourself try to understand it, okay? So here is another example, and it's really simple. So we start from the right to compare P and N, no work, we skip it. So got E and N, no work, but E exists, so we try to island these two letters. We got T and E island here, and so we compare D and N, now match D not exists, skip it. And we got A and N mismatch, but A exists in the pattern, so we island A and A here. Okay, we can see. Great, isn't it? So it's N and A match, A and A match, E and E and L and L. Right, perfect. So we have the answer now, and I hope you can have a clear understanding of this algorithm now. And now what finally I'm going to talk about is the complexity of this BMH, okay? So the worst case is big O-N-F compression. So you may ask, how do you get this? Okay, let's just I will just give you an example, okay, of the worst case. Let's just assume the pattern is equal to, oops, not fast. Okay, let's just assume pattern is equal to B, A, a lot of A, and the size of it is M. So we have 1B and -1 A, right? Okay, and the string stores a lot of N, actually NN, right? And if we want to find the pattern in it, we first start to compare, right? We find ourselves compare like M -1 times until we find that the B is mismatched, right? So we can only move one step each time, because every time it's the same, because S is all the same, right? So we only can move one step each. So because of this, we need to move N times, and we need to do N-1 match every time. So it is N-1 times N-1 match, and to simplify it, we will just say it's big O-N-M, okay? So that's how we got the worst case. And for the best case, here is an example 2. We let the pattern be the AB, right? And assume its size is M, and the string is going to be C, a lot of C, and the last two letters is AB, and the size of N, okay? So we put AB here to compare them, and we find that the first the B is mismatched, right? So we can skip two letters, and because they are all the same, and at each time we can skip M letters, and until we get here and we find ourselves get a match, which means there are N letters in the string, and each time we skip M letters, and we have N over M times skip, right? So that's how we got the best case. The complexity of the best case is actually big O(n) over I compressions, and this BMH algorithm works quite fast in practice, and you can just write your own coding say. And actually I have write one here, but I don't have time to explain to you, so I'll just briefly show you, okay? And that's all of my presentation, and thanks for watching.